A single hurricane can collapse a nation's infrastructure in 72 hours. Roads vanish, power grids fail, coastlines redraw themselves, and then the storm moves on. That is the key detail most people miss. It moves on. The worst weather systems in recorded human history are temporary, regional, contained. They arrive, they destroy, and they leave. Now remove that last part. Imagine a storm that does not leave. A system so large it cannot be classified as weather in any modern sense. A rotating atmospheric engine covering not a city, not a coastline, not even a country, but an entire continent. Sustained, feeding, growing, for weeks, for months, for decades. That is not science fiction. That is Earth's actual atmospheric history. And the question is not whether storms like that existed. The evidence confirms they did. The question is what kind of planet produces them, and whether the conditions that built them are as distant as we assume. Modern meteorology defines a Category 5 hurricane by wind speeds exceeding 157 miles per hour. At that threshold, reinforced structures collapse. Storm surge swallows cities. A single such system over the Gulf of Mexico generates enough kinetic energy to power the entire United States electrical grid for years. That is one storm. A temporary one. During the Carboniferous period, roughly 300 million years ago, Earth's atmosphere contained nearly double the oxygen present today. Equatorial ocean surface temperatures regularly exceeded 35 degrees Celsius. Temperature gradients between equatorial and polar zones were steeper, more extreme, and more unstable than anything modern climate science has modeled in recorded history. These were not the conditions that produce occasional severe weather. These were the conditions that produce something else entirely, a different category of atmospheric reality. The Carboniferous world was a pressure cooker with no release valve. Dense forests covered vast stretches of land, pumping oxygen into an already saturated atmosphere. The oceans were warmer at depth. Heat transfer between ocean surface and atmosphere operated at intensities modern storm science has no direct equivalent for. And when energy systems that large begin to rotate, they do not behave like hurricanes. They behave like planetary weather regimes. Self-sustaining, continent-scale atmospheric structures that would make a Category 5 hurricane look like a passing afternoon shower. But that's not the real problem. The problem is not just scale, it is duration. A modern hurricane draws its power from warm ocean surface water. As it moves over land or cooler water, it weakens. The energy source is cut off. The system collapses. This is why storms die. They consume their fuel and move into environments that cannot sustain them. Ancient Earth did not offer that exit. The warm surface waters were not localized, they were global. A storm system tracking across Panthalassa, the super ocean surrounding Pangea during the Permian period, had access to an essentially unlimited thermal reservoir. There was no cold water waiting to drain its energy. There was no land corridor narrow enough to interrupt its rotation. There was only more warm ocean, more heat transfer, more instability. The storm did not weaken because its fuel supply never ended. Paleoclimatologists studying the sediment layers of the Permian have found evidence of erosion patterns inconsistent with normal precipitation events. Wind-driven deposits that modern researchers struggle to explain through any storm system currently observed. Layers of material displaced across distances implying sustained, directional winds of extraordinary velocity operating over timescales far longer than any documented modern weather event. These are not theoretical markers. They are the fingerprints, not of a hurricane that passed through, but of a system that stayed. During the Permian Triassic boundary, approximately 252 million years ago, Earth lost more than 90% of all marine species and roughly 70% of terrestrial vertebrates in the most catastrophic extinction event in the planet's history. Volcanic eruptions from the Siberian traps injected enormous quantities of carbon dioxide and sulfur into the atmosphere over a period that, geologically speaking, was almost instantaneous. Global temperatures spiked, ocean chemistry destabilized, and above all of it, the atmosphere reorganized into configurations modern meteorology does not have adequate language to describe. It gets worse. In the 1990s, MIT atmospheric scientist Carrie Emanuel developed a theoretical model for a storm class never observed in human history, but physically plausible under the right thermal conditions. He called them Hypercanes. A hypercane is not simply a larger hurricane. It is a fundamentally different atmospheric structure. A storm system that forms when ocean surface temperatures exceed approximately 50 degrees Celsius, generating a vertical atmospheric column that punches through the stratosphere itself. Wind speeds in a mature hypercane would not register on any modern scale. Emanuel's models suggested sustained winds exceeding 500 miles per hour within the storm's central column. The pressure gradient at the eye would be so extreme that the system would draw stratospheric air downward, injecting it into the lower atmosphere and disrupting the ozone layer across its entire operational footprint. A single hypercane could chemically alter the atmosphere of an entire hemisphere while it operated. And under the thermal conditions present at certain periods in Earth's ancient past, conditions not speculative but documented in the geological record, the ocean temperatures required to sustain one were not anomalous. They were, in some regions, the baseline. And this changes everything about how we understand Earth's atmospheric past. There is a particular image that deep-time climate modelers keep returning to: Earth from above. Not the blue marble of modern photographs with its clean separation of land and ocean, and the scattered white spirals of familiar weather. A different Earth. An Earth where cloud cover is not scattered but layered, where the spiral structures are not regional but continental in footprint, where looking down from orbital distance you cannot clearly identify the coastline of Pangea because the atmospheric system rotating above it is larger than the continent beneath, where the storm and the planet have become, in some meaningful sense, the same object. That image is not artistic extrapolation. It is a reconstruction built from proxy data, isotope ratios, sediment displacement, fossilized wind patterns locked into ancient stone. These systems were real. They operated for durations we have no modern analog for. And the life that existed during those eras did not survive them unmodified. The sustained pressure to adapt or disappear under continent-scale atmospheric violence was among the most powerful evolutionary forces this planet has ever produced. We tend to think of climate and weather as background conditions, the stage on which life plays out. But in certain eras, the atmosphere was not the background. It was the dominant force. It did not frame events, it was the event. A planetary weather regime lasting decades would not be something organisms adapted around. It would be the primary filter determining which organisms survived at all. The storm would not be a disruption to normal conditions. It would be the normal condition, Everything alive would exist in permanent relationship to its violence, its heat gradients, its chemical output, its capacity to reshape coastlines and redirect rivers and strip topsoil from continental interiors. Modern civilization was built inside a meteorological window of extraordinary calm. The Holocene, beginning roughly 11,700 years ago, has been, by deep time standards, one of the most atmospherically stable periods in Earth's 4.5 billion year history. Our cities, our agriculture, our entire concept of a livable planet was constructed during an exception. We built everything we have during an exception, and then we called the exception normal. The storms we fear today, the Category 5s, the super typhoons, the 500-year flood events, are disturbances within a stable system. They arrive, cause catastrophic damage by human standards, and resolve. The systems that dominated Earth during the Carboniferous, the Permian, the thermal maxima of the early Eocene, those were not disturbances within a stable system. There was no stable system to disturb. The violence was the system. The storm was the atmosphere in its natural operating state under those thermal conditions. What survived was not simply lucky, it was filtered. Rebuilt at the molecular level by sustained exposure to conditions that would classify, by any modern emergency management framework, as the permanent end of the world. Some storms were not weather, they were regimes. There is a number that atmospheric scientists treat as a kind of threshold. Not a boundary in any official classification system, not a category on any public storm scale. A number that exists in theoretical models and peer-reviewed papers, and the quiet calculations of researchers who study what weather becomes when the planet stops cooperating. That number is 50. 50 degrees Celsius at the ocean surface. Below it, storms behave in ways we recognize. They organize, intensify, make landfall, dissipate. The physics is brutal but comprehensible. Above it, the physics does not break, but it produces something the modern atmosphere has never shown us. Something that has no name in any emergency management database. No historical record in any human civilization. Only a theoretical designation, a set of model outputs, and a geological past that suggests it was once not theoretical at all. Carrie Emanuel named it the Hypercane. And what that word describes should not, by the standards of the world we currently inhabit, be possible. To understand why, start with the mechanism that drives every storm on Earth. Warm ocean water evaporates. That water vapor rises. As it rises and cools, it releases latent heat, the energy stored during evaporation. And that heat drives further uplift. The rotating column intensifies. The pressure at the center drops. More surface air rushes in to replace what has risen. The storm feeds itself through this cycle, pulling energy continuously from the thermal reservoir below. This is why hurricane forecasters watch sea surface temperatures so closely. Warm water is fuel. The warmer the water, the more fuel available, the more powerful the system that forms above it. Now, raise the ocean surface temperature to 50 degrees Celsius. The evaporation rate does not increase linearly. It accelerates in ways the standard hurricane energy equations were not designed to accommodate. The volume of water vapor entering the atmospheric column becomes so extreme that the vertical velocity of rising air inside the storm core reaches speeds that carry it not simply into the upper troposphere, the ceiling of most weather systems, but through it entirely, into the stratosphere. The Hypercane does not respect the tropopause, the boundary layer that contains conventional weather. It punches through it, and in doing so, it stops being a weather event in any meaningful category and becomes something closer to a geological force operating through the medium of air. Emmanuel's models calculated sustained surface wind speeds exceeding 500 miles per hour in a fully developed hypercane. The pressure differential at the storm's center would be so extreme, it falls outside the range of any instrument currently deployed in hurricane reconnaissance. The eye wall, because in a conventional hurricane, a ring of violent convection surrounding a zone of eerie calm, would in a hypercane become a vertical structure of such intensity that the distinction between eye and wall would lose practical meaning. The entire central column would be a single coherent engine of atmospheric violence, self-sustaining as long as the thermal source below it remained. But that's not the real problem. The problem is what happens above the storm. When the hypercane column breaches the stratosphere, it does not simply vent energy upward and dissipate. It injects. Water vapor, massive quantities of it, is carried into a region of the atmosphere where water vapor does not naturally belong in those concentrations. The stratosphere is dry. Its chemistry is built around that dryness. Water vapor introduced at stratospheric altitude reacts with existing compounds, and in sufficient quantities it begins to catalyze the destruction of ozone. Not over the storm's immediate footprint. Over the hemisphere. A sustained hypercane operating for weeks would not simply damage infrastructure in its path. It would begin dismantling the atmospheric shield protecting the entire sunlit half of the planet from ultraviolet radiation. The storm below would be catastrophic. What it triggers above would be systemic. This is where the science intersects with the geological record in ways that are difficult to dismiss. After the Chicxulub impact event 66 million years ago, global average temperatures spiked within a compressed geological time frame as the debris cloud thinned and the greenhouse gases released by the impact's thermal shock began their work. Ocean surface temperatures in equatorial and mid-latitude zones rose far beyond anything the modern ocean experiences. Paleothermometry data, chemical signatures locked into ancient sediment and fossil shells, indicate surface temperatures in certain ocean basins approaching, and in some estimates exceeding the Hypercane formation threshold. Not briefly, not as a transient anomaly, for extended periods during which the biosphere was already under collapse-level stress from every other direction simultaneously. And above those superheated oceans, the atmospheric conditions required to generate Hypercane-class systems were not absent. They were present. The storms may not have been a side effect of the impact crisis. They may have been one of its primary mechanisms of destruction. It gets worse. The Chicxulub scenario is dramatic, but it is not the only pathway to Hypercane conditions. The Permian Triassic extinction event, which preceded the asteroid impact by nearly 190 million years and exceeded it in biological devastation, involved ocean warming, driven not by a single impact but by sustained volcanism. The Siberian traps erupted over a period that deposited more volcanic material than any other event in the last 500 million years. Carbon dioxide concentrations rose. Methane hydrates destabilized on ocean floors and vented. Ocean temperatures climbed not in a sudden spike but in a prolonged escalation. A slow thermal loading that gave the atmosphere time to reorganize around the new energy budget. In the warm, shallow epicontinental seas that dotted the Permian world, temperatures rose toward and potentially past the critical threshold. Not everywhere, not all at once, but enough. In enough places, for long enough. The storm systems that could form over those conditions were not brief. They were recurrent, seasonal in the way that monsoons are seasonal. Not a single event, but a regime, reliably reforming as long as the thermal conditions persisted. And this changes everything about how we read the extinction record. Paleontologists studying Permian Triassic boundary sites have long noted patterns in the fossil record that resist clean explanation through temperature alone. Species that appear to have had some thermal tolerance still vanish. Ecosystems in regions that should have been climatically buffered show collapse signatures aligned with the extinction horizon. If Hypercane-class storms were operating over the superheated Permian oceans and injecting stratospheric water vapor at the scale Emmanuel's models suggest, the ultraviolet damage cascading across the hemisphere would not discriminate between thermally stressed and thermally buffered regions. The ozone destruction would be global in its reach, even if the storms themselves were geographically constrained. Photosynthesis fails under sustained elevated UV phytoplankton. The foundational layer of oceanic food webs collapse first. And when phytoplankton collapse, the cascade moves upward through every trophic level with a speed and thoroughness that mirrors what the extinction record actually shows. The storm is not just destroying things in its path. The storm is breaking the sky above everything else. There is a specific visual that atmospheric scientists use when they model hypercane cross-sections. Rendered in false color, the vertical column of a fully developed system looks less like a hurricane and more like something architectural. A tower of cloud and energy extending from the ocean surface to altitudes of 40 kilometers and beyond, its internal structure divided into concentric zones of increasing violence, its upper reaches spreading into the stratosphere in a canopy of injected vapor that fans outward for thousands of kilometers in every direction. The storm below is terrifying in the conventional sense. The canopy above is quiet, diffuse, invisible from the ground. And it is the canopy that does the systemic work. The ground-level destruction ends when the storm moves or weakens. The stratospheric injection lingers. The chemistry it initiates continues for months after the storm that caused it has dissipated. You cannot see it happening. There is no wind, no rain, no dramatic atmospheric violence to register. Just altered photochemistry in the upper atmosphere, working silently through the ozone layer while the surface below adjusts to increased ultraviolet flux without understanding why. This is the element of the Hypercane scenario that researchers find most disquieting. Not the wind speeds, though those are beyond any modern frame of reference. Not the storm surge, though a hypercane making landfall would reshape coastlines at continental scale. It is the delayed, distributed, invisible damage mechanism operating far above the storm itself. A hurricane you can model, track, survive, rebuild from. An ozone depletion event spanning a hemisphere, initiated by water vapor injection from a storm system that no longer exists, affecting photosynthesis and UV exposure across millions of square kilometers for a duration no modern risk framework has ever been asked to evaluate. That is something different. That is a consequence architecture unlike anything in human experience or institutional memory. The modern atmosphere will not produce a hypercane. The ocean surface temperatures required to initiate one do not exist in the current climate system. The Holocene's thermal budget, even accounting for ongoing warming trends, remains far below the threshold. This is not reassuring in the way it might initially sound, because the distance between current ocean temperatures and that threshold is measured in degrees, and degrees are not fixed in Earth's history. They are a variable. The geological record does not show a planet that maintains safe thermal margins as a permanent feature. It shows a planet that has repeatedly crossed them, reorganized its atmospheric physics around the new conditions, and produced weather regimes that killed most of what was living at the time. The Hypercane is not a relic of scientific curiosity. It is a documented physical possibility inhabiting the same atmosphere we breathe, waiting for the thermal conditions that have historically summoned it more than once. When oceans boiled, the sky broke. Consider what it means to have never seen a clear sky. Not as metaphor, not as a thought experiment about light pollution or cloud cover on a given afternoon. As a literal biological condition. You are born under a sky that does not clear. Your parents were born under a sky that did not clear. The generation before them and the generation before that, extending back through every human lifetime your memory can reach, none of them ever saw direct sunlight through open air. The cloud layer is not seasonal. It is not regional. It is the permanent state of the atmosphere. The sun exists as a diffuse brightening somewhere above an unbroken ceiling of gray. Rain falls not in storms that pass, but in patterns so persistent and so widespread that the word storm loses its meaning. There is no after the storm. There is only the storm, and the question of whether it will intensify today or remain at its current level of violence. This is not a hypothetical designed to produce existential discomfort. It is a description of conditions that Earth's surface has repeatedly hosted. Not briefly, not as geological instants, as sustained atmospheric regimes operating across timescales that dwarf the entire span of human civilization multiple times over. The sky across certain chapters of this planet's history did not clear. Not for years, not for centuries. The clearing, when it eventually came, was itself the anomaly. The mechanism that produces this is not a single catastrophic event. It is something more insidious. Climate systems contain feedback structures, reinforcing loops where a change in one variable amplifies changes in others, which amplify the first, which amplify the others further. Under normal conditions, these loops are constrained by balancing mechanisms that prevent runaway behavior. Temperature rises, ice melts. Albedo decreases, temperature rises further. But eventually radiative cooling increases, the system finds a new equilibrium, and the loop closes. This is how planetary climate self-regulates across long timescales. The key word is eventually. Eventually can mean thousands of years. And in the space between trigger and equilibrium, the atmosphere does not wait patiently. It reorganizes. And what it reorganizes into under sufficient thermal and circulatory stress is something that does not resemble weather in any modern sense. Pangea presented the atmosphere with a circulatory problem it had never encountered before, and has not encountered since. A single continuous landmass stretching from pole to pole, surrounded by a single continuous superocean, creates atmospheric dynamics without modern analog. The normal mechanism for redistributing heat, warm equatorial air moving poleward over alternating land and ocean surfaces, exchanging energy with the sea, descending, returning, could not operate normally over Pangea's interior. The continental interior was simply too large, too far from any moderating oceanic influence. Surface temperatures in the deep interior of Pangea during the Permian period swung between extremes that no continental interior today approaches. Summer heating was extreme. Winter cooling was extreme. The pressure gradients generated by these swings drove wind systems of a scale and consistency that modern meteorology classifies as mega monsoons. Not the seasonal monsoon circulations of South Asia or West Africa, which are themselves among the most powerful recurring weather systems on the present Earth, but systems an order of magnitude larger, operating over a landmass an order of magnitude more vast, sustaining themselves through circulation dynamics that had no coastline close enough to interrupt them. But that's not the real problem. The real problem is not the wind, it is the lock. Atmospheric circulation patterns are not infinitely flexible. They prefer certain configurations, stable arrangements of pressure systems, jet streams, and thermal gradients that tend to persist once established. The modern atmosphere shifts between configurations seasonally, driven by the orbital cycle and the thermal contrast between land and ocean. But when the underlying thermal geometry is extreme enough, the circulation can lock. It settles into a configuration that reinforces itself, where the very conditions the circulation produces, concentrated heating, moisture distribution, pressure gradient maintenance, are exactly the conditions required to sustain that same circulation. The loop closes inward, the pattern becomes self-perpetuating, and nothing short of a fundamental change in the thermal geometry, a change that itself requires geological timescales to develop, is sufficient to unlock it. During Snowball Earth, approximately 700 million years ago, the planet's surface froze nearly to the equator. Ice covered the oceans. Albedo feedback drove temperatures to levels incompatible with liquid surface water across most of the planet. And then, over millions of years, volcanic outgassing did what it always does. It continued. Carbon dioxide accumulated in an atmosphere with no liquid water and no silicate weathering to remove it. The concentration built and built until the greenhouse effect finally overwhelmed the ice albedo feedback and the planet began to thaw. What happened next was not a gentle warming. It was a thermal detonation. Ice sheets that had been locked in place for tens of millions of years melted in a geological instant. The ocean surface, transitioning from near freezing to dramatically warmed conditions across a compressed time frame, generated evaporation rates and temperature gradients that the newly liberated atmosphere could not process through normal circulatory channels. The storms that formed during the Snowball Earth deglaciation were not simply large. They were the expression of a planet attempting to redistribute an enormous accumulated thermal imbalance through the only mechanism available to it. Atmospheric circulation pushed to operational extremes. It gets worse. Acid rain is a phrase familiar from 20th century industrial pollution discourse. Sulfur dioxide and nitrogen oxides from combustion sources dissolving into precipitation, lowering its pH, damaging ecosystems, corroding surfaces. A serious environmental problem with measurable ecological consequences. A solvable human-scale problem. Now, scale the sulfur source from industrial emissions to the Siberian traps. From decades of industrial activity to hundreds of thousands of years of continuous, large, igneous province volcanism. The sulfur dioxide injected into the Permian atmosphere by sustained volcanic eruption did not produce acid rain in the sense familiar from the late 20th century. It produced acid precipitation events so chemically aggressive that fossilized evidence of their impact on contemporaneous vegetation shows structural damage inconsistent with any modern analog. Leaves preserved in Permian boundary sediments carry chemical signatures indicating pH exposures that would dissolve carbonate shells and suppress photosynthesis across entire continental regions. This was not a regional pollution event. It was a global atmospheric chemistry modification operating alongside the temperature spike, the ocean anoxia, and whatever storm systems the superheated equatorial oceans were generating simultaneously. The sky during the Permian-Triassic boundary was not simply dark or turbulent, it was chemically hostile. Precipitation falling through it was not water in any biologically neutral sense. It was a dilute acid solution descending through an atmosphere laden with sulfur compounds onto ecosystems already under thermal and UV stress. The combination did not add linearly. Each stressor amplified the vulnerability to the others. Organisms weakened by thermal stress absorbed acid precipitation damage more rapidly. Ecosystems stripped of canopy cover by acid damage absorbed more UV radiation. Reduced photosynthesis weakened the carbon cycle's capacity to buffer further. CO2 increases. The atmosphere, the ocean, and the biosphere were locked in a mutually reinforcing collapse, and the weather operating through it was not incidental to that collapse. It was a mechanism within it, and this changes everything about how we define the word catastrophe. Modern catastrophe has a shape we recognize. An acute event, earthquake, eruption, impact, flood, causes massive immediate damage. The acute phase ends, recovery begins. The catastrophe is bounded in time. It has a before, a during, and an after. Everything in human history, including the worst events our species has documented, fits this template. Even the Black Death, which killed a third of Europe's population over several years, had an after. The atmosphere during the Permian-Triassic boundary did not offer an after. The circulation lock, the acid precipitation, the thermal instability, the UV exposure from ozone disruption, these were not sequential catastrophes, each with its own after. They were concurrent and mutually reinforcing for a duration, tens of thousands of years that erases any meaningful distinction between the event and the new normal. The catastrophe did not end, it became the climate, and organisms that could not persist inside that climate, which was nearly all of them, did not wait for recovery. They were simply filtered out of the biological record. What survived was not, in most cases, the dominant, not the most complex, not the most specialized. Survivorship through a multi-century or multi-millennial atmospheric regime of that character favors different traits than normal ecological competition. It favors tolerance of chemical stress, metabolic flexibility, reproductive speed, geographic distribution wide enough that no single regional atmospheric event can eliminate the entire population. The organisms that emerged from the Permian-Triassic extinction to populate the Triassic world were not the winners of the previous era's competition. They were the organisms that the locked circulation, the acid sky, and the centuries of atmospheric instability had failed to kill. The difference matters. Evolution is not progress toward complexity and dominance. It is, in catastrophic intervals, a record of what the atmosphere could not finish. We inherit a world shaped by those intervals, the evolutionary lineages that produced complex vertebrate life, including our own, trace back through a series of narrow passages, each defined by atmospheric events that came close to erasing everything that preceded them. The clear skies of the Holocene, under which all of human civilization developed, are a kind of amnesia. They have let us forget that the atmosphere has a different mode, that it can lock, that it can sustain conditions no modern risk framework was designed to evaluate, that the sky in certain chapters of this planet's long history simply did not reset. the sky forgot how to stop. The shape of a continent is not passive. It does not simply sit beneath the atmosphere, inert, a stage for weather to perform upon. It interacts, it generates. It imposes geometry on atmospheric circulation, the way a lens imposes geometry on light. Bending, concentrating, redirecting energy flows that would otherwise distribute evenly across a spherical surface. The coastlines of modern continents create pressure gradients. Their mountain ranges deflect jet streams. Their interior plains generate convective systems. Their desert surfaces superheat the boundary layer. All of this is well documented. All of it shapes weather in ways meteorologists model with precision. And all of it, every mechanism by which the modern continents influence modern weather, operated during the Permian at a scale so far beyond current conditions that comparison becomes almost misleading. Because during the Permian, there was one continent, not several large landmasses separated by ocean basins that allow heat exchange, moisture circulation, and pressure equalization across the globe. 1. A single continuous mass of land covering nearly a third of the planet's surface, stretching from pole to pole, surrounded on all sides by a single ocean so vast it covered the remaining two-thirds. Pangea. And the atmosphere above it did not behave like a scaled-up version of anything the modern world produces. It behaved like a different system operating under different rules, generating different structures, sustaining different regimes. The continent was not simply large, it was, in atmospheric terms, an engine. And like any engine, what it produced depended entirely on the thermal differentials it was designed, by geology and orbital mechanics and the sheer physics of its size, to generate. Start with the interior. The moderating effect of the ocean on terrestrial climate is not subtle. Coastal regions experience smaller temperature swings because water absorbs and releases heat slowly. The ocean acts as a thermal buffer, preventing the extreme heating and cooling that land surfaces, which respond rapidly to incoming and outgoing radiation, would otherwise experience. Modern continental interiors, the Central Asian steppe, the American Great Plains, the Saharan interior, already show the limits of this buffering effect. They swing harder between summer and winter than coastal regions. They produce more extreme convective events. The further from the ocean, the more extreme the seasonal temperature range. In the modern world, no point on any continent is more than roughly 2,500 kilometers from a coastline. The deep interior of Pangea during the Permian was more than 5,000 kilometers from the nearest ocean in multiple directions simultaneously. Nothing alive today, no ecosystem on the modern Earth, exists under those conditions. The thermal behavior of that interior had no moderating influence anywhere near it. Summer surface temperatures in the Pangean interior almost certainly exceeded 60 degrees Celsius. Winter temperatures in high-latitude interior zones dropped to conditions comparable to the modern Antarctic interior. The swing between those extremes, operating over the course of a single year, generated pressure gradients that modern atmospheric science classifies as the driving mechanism behind the most powerful recurrent circulation system the planet has produced in the last 250 million years. But that's not the real problem. The real problem is what happens at the coast. Where the superheated Pangean interior met the coastline of Panthalassa, the surrounding superocean, the thermal contrast was not a gradient, it was a wall. Hot, dry, dense air over the interior. Warm, saturated air over the ocean. The pressure differential between these two systems did not produce a gentle onshore breeze. It produced a circulation response scaled to the contrast that generated it. And the contrast was extreme in both directions simultaneously. The summer monsoon flow that developed along Pangea's coast was not a regional circulation. It was continental in scope, drawing moisture-laden air from Panthalassa deep into the interior along convergence lines that stretched for thousands of kilometers, generating precipitation events over desert regions that had received no rain for months. The winter outflow reversed the pattern, driving cold continental air offshore with a force that restructured the ocean's surface circulation across vast stretches of the surrounding sea. Paleoclimatologists studying Permian sediments have found evidence of these mega-monsoon cycles encoded in the rock itself. Alternating layers of wind-blown desert deposits and flood-generated sediment stacked in sequences indicating seasonal switches between conditions of absolute aridity and extraordinary precipitation intensity. Not year to year, season to season. The same region that baked under 60-degree surface temperatures in summer received precipitation events of a violence and volume that modern hydrology has no direct equivalent for when the monsoon circulation reversed. The desert storms generated in the transition between these two regimes. The dust events and sand transport systems activated by the pressure gradient reversals covered not hundreds but potentially thousands of kilometers of Pangean interior. A single convective system forming along a Permian desert front could carry sufficient particulate material to deposit recognizable sediment layers across a region the size of modern Europe. It gets worse. The coastal zones where Panthalassa met Pangea were not passive receiving environments for the mega-monsoon circulation. They were active participants in a feedback structure that amplified the very gradients generating the circulation. As warm, humid air from the ocean moved inland and rose along the coastal convergence zones, it released latent heat, the same mechanism driving all convective storms. Operating here at continental scale, that released heat further destabilized the atmosphere above the coast, intensifying the updraft, drawing more oceanic air inland, releasing more latent heat. The coastal cyclones generated along Pangea's equatorial margins were not simply large hurricanes. They were systems forming within an already supercharged atmospheric environment, feeding on thermal gradients that extended from the ocean surface through the entire depth of the troposphere, organized by a continental geometry that provided no mechanism for dissipation. A coastal cyclone tracking along the Pangean shoreline did not encounter the fragmented coastline of the modern tropics. Bays, peninsulas, island chains that disrupt circulation and limit system scale. It encountered a continuous coast, a consistent thermal gradient, and an interior that was, if anything, drawing it further onshore by maintaining the pressure differential that was organizing it in the first place. Where multiple coastal systems converged, at the corners of Pangea's roughly triangular northern mass, or along the junction zones between the northern Laurasia section and the southern Gondwana component before final assembly, the atmospheric conditions became something that numerical climate models struggled to represent, without generating instabilities in the model itself. Not because the physics breaks down, because the physics produces outputs that the model architectures, calibrated against modern atmospheric conditions, are not designed to process. The researchers who have attempted full Pangea atmospheric reconstructions consistently note that their model runs require intervention to prevent cascade failures. Not physical cascade failures, but numerical ones, where the simulated energy concentration in certain atmospheric zones exceeds the model's operating assumptions and the computation becomes unstable. The real atmosphere, of course, had no such constraint. It simply produced whatever the physics demanded. And what the physics demanded in those convergence zones was extraordinary. And this changes everything about how we understand continental configuration as a climate variable. The modern scientific consensus on tectonic climate forcing focuses heavily on the position of continents relative to poles. Whether land sits at high latitudes to allow ice sheet formation, which amplifies glacial cycles. This is a legitimate and well-supported mechanism. But Pangea demonstrates a different forcing pathway, one that does not require polar land ice at all. The extreme concentration of landmass, regardless of latitude distribution, generates thermal and circulatory extremes through the pure geometry of land-sea contrast. You do not need an ice age to destabilize the atmosphere. You need a continent large enough that its interior loses thermal connection to the ocean entirely, generating gradients that the circulation must express through structures the modern atmosphere, with its fragmented, distributed continental geometry, simply cannot produce. Pangea was that experiment, run at full scale for tens of millions of years. And the atmosphere's response to it was not subtle. It was the most violent sustained circulation regime the post-Cambrian Earth has documented. The lightning record from Pangean boundary sediments deserves specific attention. Electrically activated fulgurites, tubes of fused silica created when lightning strikes sandy or silty surfaces, are found in Permian deposits at densities suggesting electrical storm activity far exceeding anything modern tropical regions generate. The atmospheric conditions driving Pangean megamonsoons would have sustained convective systems of sufficient vertical development to generate charge separation on a scale that modern thunderstorm physics typically cannot maintain for extended periods. But typical modern thunderstorms do not form within circulation systems spanning half a hemisphere. They do not have access to updraft columns sustained by the thermal differential between a continent the size of Pangea and an ocean the size of Panthalassa. The lightning storms that operated along Pangea's convergence zones were not simply intense, they were persistent, reorganizing each evening as the convective cycle reinitiated, electrifying the same corridors of unstable air across the same geographic regions for seasons at a time, in some modeling reconstructions for patterns so consistent across years that they suggest semi-permanent electrical storm belts anchored by the continental geometry itself. Stand anywhere on the Pangean interior during the Permian's peak thermal phase, and the sky above is not the sky of human experience. It is a sky organized by different rules. The horizon in multiple directions simultaneously shows the glow of lightning embedded in convective structures, too large to resolve as individual storms. The air carries the chemical signature of sustained atmospheric electrical discharge. Ozone, nitrogen oxides, the sharp metallic edge of a charged environment operating at intensities modern humans have never been exposed to outside of laboratory settings. The wind does not behave like regional weather, it behaves like something being driven by a pressure machine with a continental scale piston. The sand it carries does not drift. It moves in coherent fronts, darkening the sky from ground level to the upper troposphere, advancing across the landscape with the organized velocity of a system that has been building for weeks across thousands of kilometers of interior desert. And somewhere behind that front, over the coast you cannot see, A circulation the size of a subcontinent is organizing itself for its next iteration, drawing moisture from an ocean that has no islands, no competing pressure centers, no fragmentation to interrupt its contribution to the engine running above it. This is what a single continent does to the sky. Not gradually, not subtly, completely. One continent changed the sky. Evolution is usually explained as a competition between organisms, predator and prey, species and species, the struggle for food, for territory, for reproductive access. These are the forces biology textbooks center when they reconstruct the history of life. The visible, legible contest between living things that Darwin identified and that a century and a half of subsequent research has elaborated in extraordinary detail. The framework is accurate, it is also incomplete. Because layered beneath the biological competition, driving it from below, structuring which competitions were even possible and which organisms were available to participate in them, was a force biology textbooks treat as background. The atmosphere, the climate, the weather, not as a context for evolution, but as one of its primary mechanisms. Not a stage for natural selection to perform upon, but a selector in its own right. Indifferent, non-biological, operating across timescales that individual species cannot perceive or respond to strategically, eliminating entire lineages not because they lost a competition, but because the sky above them changed and they were not, through no fault of their own design, built for what the sky became. The Carboniferous period produced the most oxygen-rich atmosphere in Earth's history. Vast, dense forest covered the equatorial landmasses, photosynthesizing at rates the modern biosphere does not approach. Atmospheric oxygen concentrations rose to approximately 35%, compared to the modern 21%. As the carbon fixed by those forests was buried in the swampy, anoxic conditions that would eventually become the coal deposits the Industrial Revolution burned. That oxygen enrichment changed everything about the biological possibilities available to life during that period. Insects, whose respiratory systems operate through passive diffusion rather than active pumping, could scale their body size in direct proportion to available oxygen concentration. Dragonflies with wingspans exceeding 70 centimeters patrolled the Carboniferous sky. Millipedes 2 meters long moved through the forest floor. The entire arthropod body plan, constrained in the modern world by the limits of passive oxygen diffusion at 21% atmospheric concentration, was liberated by the Carboniferous oxygen surplus into a size range that has never been repeated. But that oxygen enrichment carried a cost the forest ecosystem could not fully perceive or manage. At 35% atmospheric oxygen, combustion thresholds dropped dramatically. Material that would not ignite under modern conditions burns readily. A lightning strike into a modern forest starts a fire constrained by the oxygen available to sustain it. The same lightning strike into a Carboniferous forest starts something different. A fire that, once ignited, propagates through an atmosphere so oxygen-saturated that the usual mechanisms of fire self-limitation fail. The fossilized charcoal record from the Carboniferous, in ertonite deposits found globally in coal seams, indicates a planet experiencing wildfire regimes far beyond anything the modern fire ecology literature describes. Not seasonal fires, not regional fires. Continental fire events, recurrent, sustained, driven not by drought alone, but by the fundamental atmospheric chemistry of a world with too much oxygen to safely contain the energy a lightning storm delivers into it. The lightning storms were not incidental to this. The Carboniferous atmosphere, with its dense forest cover, high oxygen content, and the circulatory dynamics of a world still in the late stages of Pangea's assembly, generated electrical storm activity at intensities the modern tropics do not match. High oxygen combined with high humidity and high convective instability over the forest canopy produced charge separation in convective systems faster and more completely than the modern atmosphere manages. The storms were more frequent. The lightning density within them was higher, and every strike delivered its ignition potential into an environment that, unlike the modern world, had no reliable mechanism for limiting what that ignition produced. The result was not a biosphere threatened by occasional fire. It was a biosphere that had evolved entirely within a fire regime, where the capacity to survive repeated burning events, to re-sprout, to disperse rapidly, to colonize freshly cleared terrain before competitors recovered, was not an advantage. It was a minimum requirement for persistence. But that's not the real problem. The real problem was what happened when the Carboniferous ended. The oxygen concentration did not remain at 35%. The burial of organic carbon that was driving the oxygen increase eventually slowed as the evolutionary innovation of lignin decomposition, organisms developing the enzymatic capacity to break down woody tissue, began returning buried carbon to the atmosphere. Oxygen levels dropped, not instantly, over millions of years, but the drop, in evolutionary terms, was rapid enough to constitute a fundamental shift in the selective environment. The giant arthropods that had scaled their bodies to the oxygen surplus could not simply shrink back down as conditions changed. Their body plans, optimized for 35% oxygen, were maladaptive at 30% and severely stressed at 25%. The Carboniferous giants did not lose a competition to smaller organisms. They lost the atmospheric conditions their existence required, and the organisms that replaced them were not their evolutionary successors. They were different lineages entirely, and ones that had maintained body plans compatible with lower oxygen concentrations throughout the high oxygen period, constrained by it, outcompeted within it, but structurally capable of persisting through the transition that eliminated their larger contemporaries. It gets worse. The Carboniferous rainforest collapse, approximately 307 million years ago, represents one of the most abrupt vegetation transitions in the fossil record. The continuous equatorial forest belt that had dominated the Carboniferous landscape fragmented into isolated patches separated by expanding seasonally dry zones. The mechanism was climatic. A shift toward more variable, more seasonally extreme conditions, driven by glacial cycles interacting with the changing atmospheric composition of the late Carboniferous. But the effect on the fauna embedded in that forest ecosystem was not gradual. It was a fragmentation event. The rapid conversion of a continuous habitat into an archipelago of isolated patches, each too small to sustain the full Carboniferous ecological community, but large enough to sustain fragments of it under different selective pressures, in isolation from each other. Amphibians, the dominant terrestrial vertebrates of the Carboniferous, were critically dependent on the continuous forest for moisture, their permeable skin, their reproductive requirement for standing water, their thermal sensitivity. All of these constraints were manageable within the humid, thermally buffered environment of the continuous rainforest belt. In the fragmented landscape of the late Carboniferous and early Permian, they were not. The populations isolated in each forest fragment were no longer part of a continuous gene pool. They were evolving independently under local conditions, with no possibility of rescue from adjacent populations when local conditions deteriorated. Some lineages and some fragments found those conditions tolerable. Many did not. The amphibian diversity of the Carboniferous did not transition smoothly into the Permian. It collapsed through a combination of direct habitat loss and evolutionary isolation, leaving a reduced and restructured fauna adapted to a world that no longer resembled the one that had produced them. And this changes everything about how we read the evolutionary record. The lineages that emerged from the Carboniferous collapse with expanded ecological range were not the ones that had dominated the high oxygen, high humidity, continuous forest environment. They were the ones that had operated at the margins of that environment. The early amniotes, whose eggs could be laid on dry land, whose skin was less permeable, whose metabolic flexibility allowed survival in the more variable conditions of the forest edge and the seasonally dry zones. The atmospheric shift did not simply clear space for them. It restructured the entire selective landscape in their favor, turning their previously marginal adaptations into central advantages and turning the previously central adaptations of the Carboniferous dominance into liabilities. Evolution did not select for the best organisms in any absolute sense. It selected for the best fit to the atmospheric conditions that happened to be operating at that moment. And the atmospheric conditions were not stable. They were a moving target, driven by oxygen dynamics, volcanic forcing, orbital cycles, and the circulatory consequences of a shifting continental geometry, none of which biological lineages could anticipate or strategically prepare for. The fossil transition zones that mark major extinction and diversification events share a consistent characteristic when examined at high resolution. The organisms that persist through them are not, as a general pattern, the most complex, the most specialized, or the most ecologically dominant organisms of the preceding era. They are the most tolerant of variability, the ones with the widest thermal ranges, the broadest dietary flexibility, the reproductive strategies that could sustain population viability through extended periods of reduced resource availability, the body plans that could function across a range of atmospheric oxygen concentrations rather than being optimized for a single one. These are not the traits that win ecological competitions under stable conditions. Under stable conditions, specialists outcompete generalists. Efficiency outcompetes flexibility. Optimization outcompetes tolerance. But stability in Earth's atmospheric history is the exception, and the organisms whose lineages persisted through the unstable intervals were not the winners of the stable periods. They were the ones the stable periods had not yet eliminated. We are among them. Every complex vertebrate alive today carries evolutionary history, shaped by the atmospheric filters of the Carboniferous collapse, the Permian-Triassic boundary, the Cretaceous thermal maximum, and a dozen other intervals during which the sky stopped behaving in ways that the dominant biology of the moment was built to handle. Our thermoregulation, our metabolic flexibility, our respiratory capacity, our behavioral plasticity. These are not simply traits that emerged because they were efficient under normal conditions. They are the inherited solutions to atmospheric problems that killed everything less capable of solving them. The storms that dominated ancient Earth did not merely destroy, they designed, not intentionally, not directionally, not toward any goal, but with the absolute efficiency of a filter that passes only what can survive its conditions, whatever those conditions happen to be. The sky was not background to evolution. It was the examiner. and the exam had no mercy for specialization, built around conditions that would not last. Survival favored those who endured the sky. The question is not whether the physics still works. It does. The same atmospheric mechanics that produced hypercanes over Permian oceans, that locked Pangean circulation into decade-spanning mega-monsoon regimes, that drove Carboniferous storm systems across continental interiors without interruption, that physics has not been repealed. It is not a historical artifact. It is not a property of ancient Earth that modern Earth has outgrown. It is the physics of the atmosphere as it currently exists, operating within a thermal envelope that currently keeps it below the thresholds that activate its most extreme behaviors. The word currently is doing significant work in that sentence. And the question that climate scientists, atmospheric physicists, and a growing number of national security analysts are beginning to ask, carefully, precisely, with the methodological caution that the subject demands, is not whether extreme ancient weather could theoretically return. It is how far the current thermal envelope is from the thresholds that made it routine. The answer is not as reassuring as most public climate communication implies. Modern hurricane science already documents a clear warming signal. Sea surface temperatures in the Atlantic, Pacific, and Indian Ocean basins have risen measurably over the past century. The relationship between sea surface temperature and maximum potential hurricane intensity is not contested. Warmer water produces more energetic storms. The debate is not about the direction of the effect. It is about the magnitude, the regional distribution, and the rate of intensification. What is now emerging from the more recent modeling literature is a recognition that the relationship between ocean temperature and storm intensity is not linear across its full range. Within the temperature window familiar from modern hurricane climatology, roughly 26 to 30 degrees Celsius at the surface, intensity increases are substantial but manageable within existing frameworks. Projections for a 2-degree warmer world produce storms roughly 10 to 15% more intense than the modern baseline. Serious, costly, deadly, but not categorically different from what current infrastructure and emergency management systems were built to handle. However inadequately they handle it now. The nonlinearity begins above that window, at ocean surface temperatures approaching 35 degrees Celsius. Temperatures that do not currently exist in any hurricane-forming basin, but that are not physically impossible under high-end warming scenarios. The energy available to a developing storm system increases faster than linear projections from the cooler end of the range would suggest. The dynamics begin to shift. Intensification rates accelerate. The radius of maximum winds expands. The storm's capacity to maintain peak intensity over longer periods and across greater distances increases. These are not catastrophic departures from familiar storm behavior. They are the beginning of a continuum that, extended further along the temperature axis, eventually reaches the threshold where the system stops behaving like a large hurricane and begins behaving like something categorically different. The threshold is not a cliff edge, it is a curve that steepens, and the steepening is already, at current temperatures, underway. But that's not the real problem. The real problem is not what a warmer storm does to a coastline. Modern coastal infrastructure is already inadequate for the storms it currently faces. A Category 5 hurricane making landfall over a major coastal metropolitan area produces damage the affected region requires years to recover from, if it recovers at all in any meaningful sense of restored functional equivalence. This is already true. Climate change making such storms 15% more intense does not create a new category of civilizational risk. It accelerates and amplifies an existing one. The real problem is the infrastructure that was not built for storms at all. The systems that have never been stress tested against atmospheric violence, because they were constructed under the assumption that the atmospheric violence they needed to withstand had a defined ceiling. Power grids, water treatment systems, financial clearing networks, hospital systems, agricultural supply chains. All of these were designed within a range of anticipated disruption derived from historical storm records. And historical storm records, for the purposes of modern infrastructure planning, means the last few hundred years of documented meteorology, which is, in deep-time atmospheric terms, a sample drawn entirely from the calmest interval in millions of years of planetary history. A storm system in the 40-degree ocean surface temperature range, hypothetical at current warming levels, not hypothetical under high-end projections for the late 22nd century. Making landfall over a city the scale of Tokyo, Karachi, or New York would not produce damage comparable to historical hurricane records multiplied by some intensity factor. It would produce a qualitatively different failure mode. The wind loads exceed the engineering assumptions of virtually every structure built before the late 20th century and many built after. The storm surge, driven by a pressure differential and wind field beyond the range of existing coastal defense designs, overtops barriers engineered to historical storm surge maxima. The rainfall totals, generated by an atmospheric moisture content scaled to ocean temperatures the region has never experienced, accumulate faster than drainage infrastructure can process under any operational scenario. And these failures are not sequential, they are simultaneous. The power grid fails not after the flooding, but during the wind event. And the failure of the power grid means the pumping infrastructure that manages the flooding also fails. And the failure of the pumping infrastructure means the flooding reaches depths that the structural damage models, which assumed the pumping infrastructure would function, did not anticipate. It gets worse. The economic cascade from a single extreme atmospheric event over a globally connected major city does not stay within the physical boundaries of the affected area. Modern financial systems, logistics networks, and manufacturing supply chains are not organized to absorb the simultaneous removal of a major node. The 2011 Thailand flooding, a comparatively modest event by the standards under discussion, disrupted global hard drive manufacturing for more than a year because a concentrated geographic cluster of production facilities was damaged simultaneously. The supply chain logic that produced that vulnerability has not been restructured. It has been extended, deepened, and made more geographically concentrated in the years since. A storm system at the upper end of what warming physics could theoretically produce, tracking over one of the dozen or so cities that serve as critical nodes in the global logistics and financial network, would not produce a localized disaster. It would produce a systemic shock propagating through supply chains, insurance markets, and credit systems at a speed and scale that no existing financial stability framework was designed to manage. And this changes everything about how we frame the climate risk conversation. The standard public communication around climate change and extreme weather focuses on probability, the increase in likelihood of events within the familiar category of severe weather, expressed as percentage changes against a historical baseline. This is a legitimate and important framing. It is also insufficient because it implicitly assumes that the events in question remain within the category familiar from the historical record. Probability communication for familiar events is comprehensible and actionable. Probability communication for events that are categorically outside the historical envelope, events that exceed not just historical intensity maxima, but the engineering and institutional assumptions built around those maxima, requires a different framework. Not because the probability is necessarily high. In most near-term scenarios, it is not. But because the tail of the distribution, under sufficient warming, does not thin in the way the familiar statistical models assume. It fattens. The probability of genuinely anomalous events, events that fall outside the category of intensified but familiar weather and into the category of qualitatively different atmospheric behavior, increases faster than linear projections from the middle of the distribution suggest. The researchers who work at this end of the probability distribution do not claim that hypercane conditions are imminent. The ocean temperatures required remain far above current or near-term projected values. What they do claim is something more precise and in some ways more unsettling, that the distance between current ocean temperatures and hypercane formation thresholds is not a fixed property of the climate system. It is a variable that depends on the total atmospheric greenhouse gas concentration, the pattern of ocean heat uptake, and the operation of feedback mechanisms that are themselves sensitive to warming. The distance is currently large. It has been smaller before. There is no physical law guaranteeing it remains at its current value, and the geological record contains no example of a warming event of the current rate and trajectory that resolved without passing through significant atmospheric reorganization before equilibrium were reestablished. The cities built on coastlines around the world were positioned there during a period of extraordinary atmospheric calm. The engineering standards to which they were built were calibrated against a storm record drawn from the same period. The insurance models that price coastal risk were fitted to historical loss data from the same period. The emergency management frameworks that govern evacuation, shelter, and recovery were designed around disruption scenarios derived from the same period. None of this is unreasonable as an approach to managing known risk within a stable system. All of it becomes inadequate the moment the system is no longer stable in the way it was during the calibration period. And the calibration period, the Holocene, the last 11,700 years, is the most atmospherically stable interval in millions of years of planetary history. The modern world did not inherit a normal atmosphere. It inherited an exceptional one. And it built everything it has in the window that exception provided, without consistently asking what the atmosphere looks like when the exception ends. The ancient storms are not simply history. They are a demonstration of what the same physics, under different thermal boundary conditions, is capable of. The atmosphere that produced hypercanes over Permian oceans is the same atmosphere that produces Category 5 hurricanes over modern ones. The physics did not change. The boundary conditions changed. And boundary conditions, unlike physical laws, are subject to alteration by the accumulation of greenhouse gases at rates the geological record confirms are without precedent in the last 66 million years. The ancient sky is not safely distant. It is the destination the current trajectory points toward, at a pace that remains within the capacity of collective action to alter, but not within the capacity of wishful thinking to avoid. The storms that buried continents and broke the stratosphere and locked the sky for centuries did not require a different planet. They required a planet with different ocean temperatures, that is all. The difference between the sky we know and the sky that ended entire geological eras is measured not in planetary transformations, but in degrees. Degrees that are, at present, increasing. We are not immune to ancient skies. The asteroid gets all the attention. This is understandable. There is something cinematically satisfying about a single object, visible, finite, arriving from outside, as the explanation for mass extinction. The Chicxulub impactor was approximately 12 kilometers in diameter. It struck the Yucatan Peninsula 66 million years ago at a velocity of roughly 20 kilometers per second. The energy released in the first minutes of that event exceeded the combined yield of every nuclear weapon ever constructed by a factor so large the comparison loses meaning. The impact winter that followed, debris blocking sunlight, photosynthesis collapsing, the food web fracturing from the bottom, ended the non-avian dinosaurs and approximately 3/4 of all species then living. It is the most famous catastrophe in Earth's biological history. It is taught in schools. It has its own museum exhibits, its own documentary genre, its own cultural weight as the definitive example of sudden planetary catastrophe. And it was less destructive over geological time than the atmosphere acting alone. The Permian-Triassic extinction, which predated Chicxulub by nearly 190 million years, killed more. It eliminated over 90% of marine species and 70% of terrestrial vertebrates without any confirmed extraterrestrial mechanism. No asteroid. No impact crater of comparable scale. What it had instead was the atmosphere, reorganized by volcanic forcing into a sustained regime of thermal stress, chemical hostility, and circulatory violence that operated not for months but for tens of thousands of years. The Chicxulub event was devastating precisely because it was acute, a sudden catastrophic disruption from which the planet could begin recovering once the immediate forcing diminished. The Permian-Triassic boundary was devastating in a different, and in some ways more thorough way. Because it was not acute, it was persistent. The atmosphere did not deliver a single catastrophic blow and then allow recovery. It maintained conditions incompatible with the continuation of existing biological complexity for long enough that the existing biological complexity did not survive to recover from anything. Duration is the variable that asteroid-focused extinction narratives tend to underweight. An impact is an event. The atmosphere is a system. Events end. Systems persist until something changes the forces sustaining them. And the forces sustaining Permian-Triassic atmospheric instability, volcanic greenhouse loading, ocean thermal inertia, circulation lock patterns reinforced by their own output, were not the kind of forces that dissipate in years or decades. They were the kind of forces that require the geological equivalent of patience to resolve. Life did not wait out the Permian-Triassic boundary the way animals wait out a hurricane. It evolved through it, was filtered by it, and emerged from it as something structurally different from what had entered. Not because the survivors were superior, but because the atmosphere had operated as a selective filter for long enough to eliminate everything that could not meet its terms. But that's not the real problem. The real problem is the assumption the asteroid narrative quietly installs, that planetary catastrophe requires an external cause. That Earth, left to its own devices, tends toward conditions compatible with life as we know it, and that the disruptions severe enough to restructure the biosphere come from outside. From space. From unpredictable, unpreventable, cosmically random events that could not have been anticipated, and against which no internal planetary process offers protection. This assumption is historically inverted. The most destructive intervals in Earth's biological history were not externally caused. They were internally generated by the planet's own volcanic systems, its own ocean chemistry, its own atmospheric physics responding to the thermal boundary conditions those internal processes produced. Earth has repeatedly catastrophized itself without assistance, without external trigger, using only the mechanisms available within its own system, operating within the normal range of variation those mechanisms have always expressed across deep time. The atmosphere is the primary instrument of that self-catastrophizing capacity, not because it is malevolent or directed or in any sense intentional, but because it is the medium through which the planet's thermal energy budget is expressed at the surface, and the surface is where life lives. Tectonic forces determine the distribution of land and sea. Orbital mechanics determine the pattern of solar input. Volcanic activity determines the composition of the atmosphere over geological timescales. But it is the atmosphere that translates all of these slow, deep Earth processes into the immediate surface-level conditions that biological organisms actually experience. It is the atmosphere that receives the thermal signal from the warming ocean and converts it into storm dynamics. That absorbs the volcanic sulfur and converts it into acid precipitation. That reorganizes its circulation in response to a shifting continental geometry, and in doing so transforms a selective environment for everything living beneath it. The atmosphere is not the background against which planetary history unfolds. It is the mechanism through which planetary history reaches life. It gets worse. Human cognitive architecture is not designed to perceive systems at the scale and time scale the atmosphere operates on. We perceive events. We perceive objects. We perceive sequences with identifiable causes and effects operating within timeframes our attention can hold. A storm system lasting decades does not fit this perceptual architecture. A circulation regime sustaining itself for thousands of years is simply outside the range of anything direct human experience can calibrate against. We know these things intellectually through the proxy record of deep time science, through sediment cores and isotope ratios and fossilized wind patterns. But knowing them intellectually is different from integrating them into the intuitive model of the world that actually governs how we assess risk, make decisions, and allocate collective resources. The intuitive model is calibrated against the Holocene, against 11,700 years of atmospheric stability so complete, so consistent, so far from the thresholds that activate the atmosphere's most extreme behaviors that the stability itself has become invisible. We do not perceive it as exceptional. We perceive it as the nature of the sky, and the sky's actual nature: dynamic, sensitive to thermal forcing, capable of radical reorganization, demonstrably willing to sustain conditions incompatible with complex life or geological timescales, remains for most people most of the time genuinely abstract. And this changes everything about what kind of problem climate represents. It is not at its deepest level an environmental problem, a matter of preserving the natural world against human damage. It is not at its deepest level an economic problem, a matter of internalizing costs and correcting market failures. It is an atmospheric stability problem, a question of whether the thermal boundary conditions the current atmosphere operates within, the conditions that keep it in the mild, predictable, Holocene-like regime, remain within the range the current trajectory preserves. The atmosphere does not respond to warming gradually and proportionally across its full range of possible states. It has thresholds. Below them, change is incremental. At them, the system reorganizes. Above them, behaviors become active that the modern world has never observed, and that the engineering and institutional infrastructure of modern civilization was not built to accommodate. The question is not whether warming is occurring. The question is how the atmosphere responds to it as thermal forcing continues, and where in the curve of possible responses the current trajectory places the system. The deep time record does not offer reassurance. It offers precision. It documents with the clarity of geological evidence accumulated over billions of years exactly what the atmosphere is capable of under thermal conditions the current trajectory is moving toward, at rates the geological record has not previously recorded. That documentation is not a prediction. It is a demonstration of physical possibility, a record of what the same atmosphere, governed by the same physics, has produced when the boundary conditions were different from the ones the modern world has normalized. The ancient storms were not anomalies within a generally stable system. They were the stable system for their time. The Holocene is the anomaly. We are the species that built everything it has inside the anomaly and then forgot that anomalies, by definition, are not permanent. There is a specific quality of attention that the deep time atmospheric record seems to demand. Something between scientific precision and genuine humility. Not despair, not fatalism, not the paralysis that can accompany the recognition of forces operating at scales larger than human agency comfortably addresses, but a clear-eyed acknowledgement that the sky above any given morning is not a fixed feature of the planet. It is a current state of a dynamic system with a documented history of radical transformation, operating within boundary conditions that are themselves changing. Governed by physics that does not grant special accommodation to the civilizations that happen to exist during the particular interval when the system is calm. The blue sky of a clear day is not the sky's default. It is the sky in one of its quieter configurations. The other configurations are in the record. They are real. They shaped everything alive today through the selective pressure of their violence and their duration. And the distance between this configuration and those configurations is not geological. It is thermal. It is measurable in degrees. The sky has never been a backdrop. Not in the Carboniferous, where it electrified and burned and shaped the arthropods that filled it. Not in the Permian, where it locked into chemical hostility for tens of thousands of years and filtered the biosphere down to what could survive its terms. Not in the aftermath of Chicxulub, where it went dark and cold and restructured the available evolutionary space for everything that remained. Not now, where it absorbs the thermal consequences of a civilization that built itself inside its calmest historical interval and is now systematically loading it with energy. The sky has always been the primary force, the dominant shaper, the examiner that life has always ultimately answered to, not the other way around. Every structure we have built, every species boundary we have inherited, every evolutionary lineage that produced the complexity of life as it currently exists, all of it was built inside the atmospheric conditions that happened to be operating at the relevant moment. The conditions were not guaranteed. They were not permanent. They were the output of a system that is demonstrated, across billions of years of documented operation, its full capacity for configurations that would render the modern world unrecognizable within a human lifetime. The sky was always the architect.